Okay, so the problem is, well, we don't know betas, right? So this is just like, so the population parameters mu and sigma, we don't know the population parameters mu and sigma. This is a similar thing. We don't know the population regression parameters beta 0 and beta 1. So just like we use the point estimator, X bar for mu and S for sigma, we will find an estimator for beta 0 and beta 1, okay? So how to estimate them? Well, in fact, we did, right? How to estimate them? Well, we did. How? We just tried to fit the best line through the available data points, okay? So remember, in the previous slide, in I don't know, 5.1, we were talking about there are several points there. And what is the best point just passes through these points. We just find this point using what? SSE, remember, to minimize the errors, the sum of squared errors. In fact, when we are doing this, we were just trying to find the population regression line and an estimate of the population regression line, okay? So the B0 and B1, okay, the B0 and B1 that we found in the previous example when we are trying to find this line that passes through these points. Well, in fact, they are random variables, right? Because, for example, if you just take 25 many guys and plot them, right? And then find a line with B0 and B1, and just go to another class. Let's say this is our statistics class. Let's say this is the production planning class, okay? And if you just find another 25 many guys and plot the line, then the line that you will find is a bit different than the other, okay? So B0 and B1 here is different than the B0 and B1 here. Okay, so um, okay, so the B0 and B1 that you found in stats class will be different than B0 and B1 in the production plan class, okay? So B0 and B1 at each class, at each sample will be different than each other. So, well, in fact, these B0 and B1 are random variables, okay? And as you might guess, they should be estimating something. Well, in fact, B0, which was the intercept of the line that we found using minimizing SSE, is an estimator for beta 0, which is the population intercept, let's say, and B1, in fact, is an estimate for beta, okay? So remember, we say B0 plus B1x. This was the line using by minimizing SSE, right? Minimizing SSE. So in fact, their estimate is for the population regression line, which is unknown bias. So this is the population regression line. So this is an estimator for beta 0, and this is an estimator for B1. Just like X bar was an estimator for mu, and S square was an estimator for sigma square, okay? Exactly the same. So just like if we just take samples from different class, we will have different X bar and different S square. And similarly, if you just take different samples from different class, you will have different set of B0 and B1s, okay, which will again estimate beta 0 and beta 1. Okay, so for example, assume we have something like this. We just take, I don't know, 30 minute observations. Well, so this red line, so this is the fitted line, okay? This is the B0 and B1. How do we find this line? We find this line by just minimizing, let me just write it here, minimize SSC and find B0 and B1, okay? And this line, this blue line, sorry, okay. Okay, that's not a big deal. So in fact, there's a problem here, I guess. So the first one, this is the fitted line, right? So the first line, okay. So this is the fitted line. This is the fitted line. And this blue is the hypothetic line, okay? So this blue line is the hypothetic line. This is the hypothetic line. Well, this is the real line that we don't know. Of course, since we are just making an example, I just write this time because I know it, because I just produced this data. This is the hypothetic line, but in real life, right? In real life, we never, we never know this. We never, sorry, let me just take my eraser there. We, um, okay. We never know the real line. We never know this, right? We never know this line. Right? The only thing that we can do is we can we can estimate we can estimate the real unknown or hypothetic line, unknown line. Okay, this is the best that we can do. Again, this is just like we don't know mu. What we can do is we can just estimate it using the x bar. Right. Now we will talk about the residuals and the errors. Okay, so what does this mean? Okay, I don't have this color. So consider the following two models. So the first model is what we call the mu of y given x, or we also show it as mu of y. That's equal to beta 0 plus beta 1x. So remember, we say y, the random variable is equal to beta 0 plus beta 1x, which is in fact the mu of y, plus the error term, right? Plus the error term. So this is the constant part, this is the constant part, and this is the random variable part, okay? So, um, so, so this is the capital letter by capital letter epsilon, which shows the random variable as a definition. So for a specific one, you can just write yi is equal to beta 0 plus beta 1 times x, okay, xi plus epsilon I, right? So this is the small epsilon. So for every observation, so every realized observation, you have a every realized observation, you have a realized error term there. Okay? But the thing is that since we don't know beta 0 and beta 1, we don't know the real value of epsilon. Okay. So another line is the estimated line. Okay, so we will use B0 and B1, okay, to estimate these lines. So what you can do is, what we can write is, let me change my color again. So you can just write, instead of B0, beta 0 and beta 1, you can just write B0 plus B1 times X. So this is equal to Y hat. Okay, so what is Y hat? Y hat, just look at here, Y hat. Y hat is an estimator for what? Is an estimator for mu of Y, or mu of Y given X, right? Just like X bar is an estimator for mu, okay? So this is an estimator for mu of y given x, or mu given y, mu of y, okay? So in fact, this is the x bar for mu of y, okay, or mu of y given x, right? So this is my x bar. This is my x bar. How do I find x bar? Generally, what we do is we just take the average of the samples. Here, we don't take the average, but we just find B0 and B1, and for each x value, I just substitute x and find the corresponding y hat. Okay. So now for any value, for example, for any student that I see, I can just write this. Y, for example, y1, let's say this is a student called, let's say, Mehmet. So y1, y Mehmet is equal to beta 0 plus beta 1 times x Mehmet. So what is x Mehmet? Let's say it's 180 plus the error term of Mehmet. Okay. So this is also equal to mu of y, or again, mu of y given x. They are the same thing, plus epsilon. This is what we call an error term, but as I said, since we don't know beta 0 and beta 1, we cannot observe it. We don't know the real value of epsilon. Or we can just write yi, the height of Mehmet, as y1 or y Mehmet is equal to b0 plus b1 xi. So I know b0 because I can estimate them using what? Using SSE, right? So these are values that we can find, okay? Times xi. So I know this value, okay? So what is this again? This is y hat, right? Y hat. Plus now I don't write epsilon I, but I write ei, right? So I can just write, well, Mehmet's height is equal to the estimator, the y hat, the estimator of the average height of students or people at this height, right, which is y hat, plus Mehmet's own error term, okay? So again, yi, the height of Mehmet is equal to the average height of people at Mehmet's height plus Mehmet's error term, okay? And Mehmet's error term is equal to yi minus y hat, I. So what is this? This is the real value. This is the height of Mehmet. So what is y hat I? Well, this is the predicted value, okay? So this is exactly the same thing, remember, that we did in the previous slides. So this is the, okay, so this is the vertical deviation between the real value and the predicted value. And this is what we call an error. And the good thing is that we can observe them, right? Because we know the predicted value, we know the real value. I can just find the difference and I can just observe the residual term, okay? Okay, so, well, the ith residual, okay, so this is the definition of the residual, is given by the difference between the real value of that observation minus its predicted value, okay? So this is a good way to illustrate the difference between the error term and the residue, okay? So assume you are given a set of data. Well, this is the real hypothetic line that you don't know. You don't know this line, right? Because it's the hypothetic line. So what you do is you just estimate it using the data that you are given. So the data that you are given is not here. Let me just put it like this. Okay, so let's say this is the data that you are given. So you just find the estimated data. So again, B0 is an estimate for beta 0, B1 is an estimate for beta 1, and Y hat is an estimate for mu of Y given X. Okay, so at every different X value, you have a different mean. Remember, at every height, you have a different mean for the weight of the students. So here, at every value of X, you have a different estimator, you have a different point estimator for the means at different height. And this is this red line now. This red line, so this red line, sorry, this red line is the estimated line, okay? So this is xi, and this is yi, right? This is from the analytical geometry. So this is yi. The difference between the yi, okay, so this one and this point, this point is, this is the y hat I, okay? And how about this point? This point is the mu of y at given xi, okay? So the difference between the yi, okay, and the estimated parameter is ei. This is the residue, okay? And the difference between the observed value and the real mean response, real mean value, okay, the difference here. So this part is the residual, and let me just change my color. This difference between here, that's called the epsilon I, okay, epsilon I. This is the error term. This is the error term. This is the difference between the mean of the weights at that particular height, okay, and the real value of that guy whose height is xi. So for example, if xi is equal to, let's say, 180 centimeters, and if this is equal to, for example, 75 kilograms, it means that, well, the real mean of kilograms of people who are 180 centimeters tall is 75 kilograms. And let's say this is the weight of me, my height is 180 centimeters. Let's say this is 83 kilograms, okay? So the difference between this is 8 kilograms, which is the error term, okay? So my error, which is the difference between the mean and my own weight is 8 kilograms. And what is why I had, so there is some data we just collected from the class, and this is the predicted line. Let's assume that says that, well, it just predicts the height, the average height of people who are at 180 centimeters as, let's say, 79 kilograms, okay? So the residual here is 4 kilograms, okay? So this is the main difference between the residuals and the errors. And again, the problem is that we don't observe the errors, we only observe the residuals. So, we have, so just like the other random variables, x bar and s, b0 and b1 has a mean, is a standard deviation, and of course is a distribution, okay? So what we will do is, just like we did in mu and sigma, right? Remember, this is mu, this is for sigma. What we did was we just use them to make confidence intervals and hypothesis tests, okay? Again, we will make hypothesis tests and build confidence intervals on beta 0 and beta 1 using what? Using B0 and B1, right? But in order to do this, we need some assumptions, okay? So what are the assumptions? Well, they are easy. Just recall how we have written the random variable y. We said that random variable y is equal to mu y plus epsilon. That's also equal to beta 0 plus beta 1 times x plus epsilon. We said that, so what does this mean? This means that, so we said that, okay, this is mu of y given x, and this was a normally distributed random variable between 0 and standard deviation sigma. So what are the assumptions? First, epsilon is a normally distributed random variable, okay, with 0 mean and with standard deviation sigma. What else? There is a linear relationship between the mean values, okay, and the independent variable x. Okay, so there's a linear relationship between them. Okay, so in fact, this is all. And one more thing is that, epsilon has a standard deviation sigma at all height levels. What does this mean? It means that the standard deviation does not increase as the height increase or decrease. Okay. So these are the assumptions. Epsilons are independent normal random variables with 0 mean and constant variance, and the mean response and the independent variable x should be linearly related. Okay. So they can be rewritten as weight and height should be linearly related. At each height value, the weights should be normally distributed, and the weights should have the same variance at each height value, and each observation must be independent of each other. Okay, so Mehmet's height should not be related or correlated with, for example, Ahmet's height. Okay? So, okay, but the problem is that, okay, so we have assumptions on the epsilon, right? Epsilon should be normally distributed with 0 and sigma and so on and so forth. But we will not observe the errors because we don't know the true, so this is the true hypothetic line. Then how can we check whether the assumptions are correct? Well, I don't know the error terms, but I will observe the residuals. So the thing is that just remember our hypothetic line, beta 0 plus beta 1 times x plus epsilon. So this is my yi, epsilon I. I said it, but I can just write it as b0 plus b1x plus the error terms, okay? So b0 is an estimator for beta 0, b1 is an estimator for beta 1, and ei, well, ei, it's not an estimator, of course, but but it will mimic the random variable epsilon I. Okay, so we cannot plot epsilon i's, but we can plot the ei's, the residuals. Okay, we will see how to make that. So we will make an example. Just remember how we just calculate the B0 and B1 using the SSE. Remember, we just take so this was the error term, right? We just square it. So yi minus yi hat. Instead of yi hat, I just write B0 minus B1 xi. Okay, so these are the residuals. Remember the vertical deviations. I just take the partial derivatives, okay, to get these values. Okay, so this is my B1, right? And this is my B0. Okay, so I don't memorize it. I don't expect you to memorize them. And this is my example. So these are the height and weight of 10 many students in our class. Please find the corresponding regression. So again, so this is what I have. mu of y given x. Well, that's equal to beta 0 plus beta 1x. Again, I don't know beta 0 and beta 1. Okay, we never know them. So instead, what I will try to do is find the estimated line, which is b0 plus b1x. How to do this? Well, just calculate the sum of xi times yi, and so on and so forth, which are given in the formula, okay, to calculate b1. So again, this thing is good for representation, okay, representation, and this formula is good for calculation, okay? They are the same thing, but this is good for calculation, this is good for representation. So using the formula above, we have B1, so this is not B1, B2, but give me a second. Okay, so this is B1, and this is B0. So what does it look like? Y hat is equal to minus 94.3, let's say, okay, 0.3, plus 0.9725, right, times x. So this is the predicted line. This is the estimated line, okay? So let's look at here. These are the data that we have. So 161, 62 points. So this is 161 centimeters, just go up. And this is 62.1 kilograms. And how about this one? Sorry, this is 165. This is 165. And how about its kilogram? That's equal to 64.4. Okay, 64.4, and so on and so forth. Okay, so what we do is just draw this line which minimizes the vertical distances. Okay? It just minimizes the vertical distances. This distance, this one, this one, this one. Again, what is this distance? This is equal to I minus y hat. Okay. We just minimize the sum of square of these errors, and it turns out that, well, the resulting line is this, okay, which is this line which passes through all of the points.